All right, hello chemistry class, and we are going to be looking at chapter 6 today, and we're going to be talking about basically chemical bonding. So we've done a lot of talk so far about the atom, the arrangement of electrons, and it is those electrons, specifically those valence electrons, remember those are the outermost electrons, that are going to be involved in forming chemical bonds so that two atoms or more than two atoms can come together and form a compound or molecule and be bonded together. Okay? Many elements like to form compounds. Here's an important point. Listen for a second. They like to form these compounds because they're able to be at a lower energy position. By themselves, they're at a higher energy position, so to speak. They have these valence electrons, and their outer shell is not full, and they would like to either give up electrons or gain electrons or share electrons to then bond with something else, some other element, some other atom, and be at a more stable position. Okay, so that's the essence of what we're talking about. Okay, you are taking notes on this video, so in your notebook, you should be writing down the information that I share with you and then uploading that into our Google Classroom and then also answering the review questions at the end of this chapter, and I will kind of help you with those. Couple introductory opening questions. Number one says here, what are valence electrons? You should remember that valence electrons are the outermost electrons at the highest energy level. Okay, they're the ones that are involved in chemical bonding. Number two says, what quantity does the electronegativity in an atom represent? It represents the pull on electrons in a chemical bond. So how well does that particular atom pull on shared electrons? Does it really want to get them close to the nucleus like small atoms do, or is it harder for it to do that like large atoms? Okay. There are two types of bonds that we're going to talk about. We're going to talk about ionic and covalent, and I'll show you in just a second how we distinguish between those. Okay. Atoms become compounds. Here's the first point that you need to understand, what a chemical bond is and how this happens. So point number one here is atoms become compounds by gaining, losing. This is your choice number one here, gaining or losing. That's your first choice. Or sharing electrons. Okay, that's your second choice. So how do atoms become compounds? Either they gain or lose. If they gain or lose electrons, that is going to form ions, and we say that you are forming an ionic bond. An ionic bond. If they're sharing electrons, we say that that is covalent. See the word co here? That means with, like together. Valent, those are your valence electrons. So you're sharing your valence electrons. So there are two choices, ionic or covalent. Ionic or covalent. Ionic is gaining and losing electrons. Covalent is sharing. And we're going to talk about why that happens and how you'll know if you have an ionic or a covalent bond. These bonds, chemical bonds, you should know this definition, have this written down in your notes. It's basically a mutual electrical attraction between the nuclei and valence electrons of different atoms. So you have atom number one here and atom number one, has protons in its nucleus, and it has electrons somewhere outside, right? Atom number two also has protons, and it has electrons. It has protons in its nucleus, and it has electrons. These protons, if these two atoms get close enough together, the protons here are going to be attracted not only to its own electrons, but to the electrons of the other atom, and vice versa. the electrons in atom number 1 are going to be attracted not just to its own protons, but to the protons of the other atom. And there's going to be an attraction between those two atoms because of the mutual pull on the protons and electrons, the protons from one atom and the electrons of the other. Okay? Now it is basically the determination of the amount of pull on these electrons. Does that mean that electrons actually get transferred from one to the other, or is the pull fairly equal and therefore they share these outer electrons? We'll talk about that. Okay? So it's basically due to the attraction between electrons and protons between two atoms. As I mentioned, there are going to be two types of bonds that we're going to talk about. You need to know these. An ionic bond is because electrons are lost or gained. Okay, this happens when you have electrons lost by one atom and gained by the other atom. And as a result, you're going to form ions, positive and negative ions, and those positive and negative ions have opposite charges and get attracted to each other. Okay? Covalent bonds, as I mentioned, covalent, valence electrons with each other. They're sharing the valence electrons. They're sharing those outer electrons. Okay? So this is when you share the electrons. Okay, so let me just show you some diagrams here. An ionic bond might be represented like this. Let's say that atom B here, likes to gain electrons. Notice it's a smaller atom. And atom A is going to lose its electrons. So let's say its outermost electrons here, I don't know how many there are, I'm just drawing a few. And atom B has some outer electrons as well, but atom B has a stronger pull on electrons because they can get closer to its nucleus. So let's say that this electron right here, one of its outer electrons, is pulled over here, okay, and is added to the already existing 6 that were there, okay? And as a result, this electron now is pulled over here, and this atom, atom A, because it lost one of the electrons, is now going to become positively charged. Now it's positively charged here, okay? Atom B is going to gain electrons, and as a result, it is going to become, it's going to gain, let's say, 1 electron, and now it has 1 more electron than the number of protons, and so it is going to become negatively charged, okay? When that happens, when there's a transfer of electrons, you're creating 2 different ions. The one that lost the electrons becomes positively charged. They're shown here with positives. The one that gained the electron here is going to become negatively charged. And opposite charges of ions, they attract to each other, okay? And as a result, they're going to be stuck together in this, basically this compound. And all the positives are going to be next to negatives, all the negatives are surrounded by positives, and you have basically what's called kind of a lattice structure of positive and negative charges in this ionic compound. This is ionic. Okay? With covalent, what happens here is that atom, in this case they say it's atom C and atom D, they both have fairly equal pulls on electrons. Maybe they're both fairly small atoms and they like to pull on electrons and get them close to the nucleus. Well, in this case, nobody's going to win outright the pull on those electrons. They're both going to kind of pull with equal force. And so what ends up happening is, yes, they get bonded together, but they end up more or less just sharing those electrons. So let's say I've got, electrons here and electrons here, and these outer electrons, they both are pulling on them because they have an attraction due to the protons, and the atom C and atom D say, you know what, we're just gonna, it's too much work to try to keep tugging war and trying to steal each other's electrons. Let's just share. So they end up sharing these electrons here, and they end up being, the shared ones are kind of in between the 2 nuclei. And the sharing of those valence electrons, we say that is covalent. Okay? Now, it's not, there are ionic compounds that are way far to one side, and like, there's a huge transfer of electrons. It's very evident. And there are covalent bonds where there's equal sharing, but a lot of times it's kind of in between. Maybe there's not an equal sharing. Maybe the electrons are pulled a little bit more to one side than the other, but it's not a pure transfer, let's say. So there's going to be somewhat in between these two. It's not all ionic or all covalent. It's somewhat in between. Sometimes, as we say, it's purely ionic if there's a strong transfer. Sometimes we say it's purely covalent if it's perfect sharing. But a lot of times it's in between these two, and there's a bit of a gradient or a scale or a spectrum in between. Okay? So the question here is it ionic or covalent? Well, there's a calculation that we can do, but there are other ways that we can determine it as well. Okay? What we can do is we can look at the electronegativity. If you remember from the previous chapter, electronegativity is basically the pull on electrons in a compound. And each element is assigned a number denoting how strong its pull is on those electrons. The higher the number, the stronger the pull on electrons in a compound. The lower the number, it means it has a weak pull. So what we do is we look at the numbers that are given for the electronegativities, and we find the difference between the electronegativities of the two atoms. And that difference is going to help us determine whether the pull is so strong in one direction that we're going to call it ionic, or is it not very strong in either direction, and then we'll say it's covalent. Okay? So here's the number that we use to determine which one it is. We take the two electronegativities, those are numbers that will be given to you, and we basically subtract the two numbers, and if the difference in electronegativity between the two atoms is 1.7 or greater, then we say that the bond is mostly ionic. So here's the line. The line right here between ionic and covalent is a difference of 1.7. So you take the electronegativity from atom number 1, the larger electronegativity, subtract the smaller electronegativity. If that difference is 1.7 or greater, then we're going to call it ionic because it's mostly ionic. It has a higher percentage of the bond is ionic. There's a stronger pull to one side. Okay, a real strong pull to one side, let's say. Okay? If it's less than 1.7, then we're going to call it covalent. We're going to say it's covalent. Okay? Now we further break down covalent into polar covalent and non-polar covalent. Let me explain. Polar, when you think of polar, you might think of a magnet, like the north and the south ends of a magnet. Okay? Or polar means like the North Pole and the South Pole. So two extremes, right? They're pulled to one side or pulled to the other side. So when we say something is a polar covalent, what that means is that you have two atoms that are, the electronegativities are close, but they're still different. And so as a result, the electrons are going to be pulled a little bit more to one side, even though they're sharing between these two atoms. Okay? The pull to one side is not so extreme that the electrons are completely transferred, but still the electrons are going to spend more time over here around one atom than they will around the other atom, because this atom, let's say in this case chlorine, has a stronger pull on electrons than hydrogen does. So if that's the case, if there's let's call it an unequal sharing, we're going to call that polar covalent, because that means electrons are going to spend more time on one side, giving this side of the compound kind of a negative charge, and this side of the compound a bit of a positive charge. Overall, the compound may be neutral, but one side of it has more electrons, the other side of it has fewer electrons, and so we say it's polar covalent. Okay? Non-polar means that there's totally equal sharing, and that usually happens between two atoms of the same element. So if you have hydrogen bonding with hydrogen, which happens all the time because hydrogen is diatomic. It appears in nature as two atoms bonded together. These middle electrons, or these shared electrons, are going to be right in between the two nuclei, shared equally, and we call that nonpolar covalent. In this case, there's not going to be a partial negative side or partial positive side to a molecule. It's all equally shared, and the electrons that are shared are going to be right in between the two nuclei. Okay? So you just need to know that we have two types, ionic and covalent, but covalent is broken down again into polar, where there's unequal sharing and the electrons kind of are edging to one side, or there's nonpolar, where the electrons are perfectly shared and the tug of war is right in the middle. Okay? Polar covalent would be like a tug of war, and one side is winning but never wins completely. Okay? If you can understand that analogy. All right. The difference here, by the way, is oh no, let's go on to the next section here. In that first section, I might ask you questions like, do this calculation, find the difference between the two electronegativities. So they would be given to you, like for sulfur and hydrogen, the two electronegativities would be given to you. You just subtract them, and you get 0.4. Well, 0.4 is less than 1.7, so it's covalent, but you have two different atoms here, two different elements, and you'll notice that even though the electronegativities are close, they're not going to be exactly the same, so we'd say it's polar covalent. Okay, polar covalent. Here, between sulfur and cesium, the difference between those two is greater than 1.7, so it's ionic. So there's going to be more of a transfer from one, it's going to go in this way, transfer from one to the other. Okay? All right. All right, in this case, let's go on now to talking a little bit more about covalent bonding and molecular compounds. Now, when we say a molecule, basically it's a neutral group, meaning it has equal number of protons and electrons, of atoms that are held together by covalence. So usually, if it's covalent, we're going to call them molecules. All right? Not a big deal. But a molecular compound is any chemical compound whose simplest units are molecules. So molecules are covalently bonded atoms. And we're going to come up with chemical formulas that indicate the relative number of each type of atom. So, you're familiar with H2O. This is a chemical compound. It tells us how many of each element are in that compound. You've got two hydrogens bonded with one oxygen. Okay? So we're going to come up with chemical formulas, or maybe we'll call them molecular formulas. Okay? In any case, there are formulas that show us how many of each atom are in that compound, okay, or in that molecule. I mentioned already diatomic. So diatomic means that you've got two atoms of the same element bonded together. So here's some examples of some molecular formulas. Here's water, as I already mentioned, H2O, and there's a diagram that kind of is trying to illustrate it. So your oxygen molecule here bonded with two hydrogens. Here you have a diatomic two atoms bonded together with the same element. So oxygen always appears as O2 in nature. An oxygen molecule bonded with another oxygen molecule. And you can bet that those valence electrons are being shared equally here. Okay? This would be an example of nonpolar covalent. Whereas water up here, hydrogen and oxygen, those are both nonmetals, and they are sharing these electrons unequally. They're sharing them, but they're pulled a little bit more towards the oxygen than they are towards the hydrogen. So in this case, the oxygen side is going to have kind of a partial negative charge to it. The hydrogen side is going to have a little partial positive. Okay? Overall, the molecule is neutral, but the one side has fewer electrons mostly residing at that end. Okay? And here you got a sugar molecule, and that looks pretty complex, but basically you've got, in one sugar molecule, you've got 12 carbon, 22 hydrogens, and 11 oxygens bonded together, all sharing electrons. Okay? All right. As mentioned, covalent bonds form from sharing electrons. It's the idea here that uh, when atoms get close together, these valence electrons are attracted not only to its own nucleus, but to the opposite nucleus over here. Okay? And the electron here is attracted to the opposite nucleus as well as its own. And so that's going to hold the electrons not only in its own atom, but it's going to attract the electrons to the other atom and hold the two atoms together. It's pretty an amazing thing. Okay. Okay. Now I mentioned they have to get pretty close to each other in order for this to happen. Obviously, if the two atoms are far apart, there's not going to be enough attraction between the valence electrons and the protons. Okay, so there's a kind of a perfect distance where they need to be in order for the bond to happen. Otherwise, if they get too close, the positive protons in both nuclei are going to repel each other. Okay, so it's kind of like your personal space. You know what? You can come talk to me, but don't stand too close. Back up, all right? But if you're standing too far away, well, it's hard to have a conversation, really, to relate then. But so you got to find that perfect distance in order to feel comfortable with somebody when you're having a conversation. It's the same idea with atoms. They find that perfect distance where the two nuclei, yes, they're trying to push each other away because they're positive protons, but they also want to be attracted to the negative electrons, and they find that perfect distance where everybody's happy and they stay bonded together. Okay? That distance is called the bond length. The bond length. And it differs for every molecule. So when two hydrogen atoms come close together, the electrons in one get attracted to the protons in the other, and vice versa. But the protons want to push each other away, as do the electrons push each other away. So they find that perfect distance, okay? And they find that perfect distance. If we could just stay at this distance, then we will be sharing, right here, we'll be sharing electrons in this region, and we'll both be attracted to those. But our nuclei will be far enough apart where we don't push each other, repel each other completely, and overall will be held together in this chemical bond. Okay? And the distance here between the two nuclei is called the bond length. That's called your bond length. Now, if you wanted to break this bond, okay, if somehow you were able to break the bond by using some energy to push them apart, the amount of energy used to break those apart is called the bond energy. So the amount of energy required to break that chemical bond and go from a chemical compound back to individual neutral atoms, that's how much energy, if that's how much energy is used, the energy that's used there to do that, that's called the bond energy. Okay? And here's a list of different bond energies. So you can see here, if we have a hydrogen-hydrogen bond, this is showing you the length of that bond in a unit called picometers. That's tiny, tiny, tiny. Okay? And here we have the average bond energy. This is, again, the energy needed in kilojoules per mole. Kilojoules per mole of atoms. How much energy it would take to break that bond. And you have a whole list here. Okay? A whole list of different ones. Now, I mentioned before that atoms like to form these bonds because it helps them be more stable. And we're going to talk about this in a little bit here, and I'm going to refer to something called the octet rule. Let me first of all give you a couple ideas here. Remember we talked about the noble gases, and the noble gases have full outer energy levels. Those outer energy levels really don't like to be messed with. If they're full, they don't like to be reduced or added to if the energy level is full. The noble gases have full outer energy levels. So for example, neon has the first energy level, has 2 electrons in it, the 1s2. The second energy level has 2 electrons in the 2s2, so you have 2 electrons there. And I'm not drawing the shapes, I'm just drawing the energy levels. And it would have 6 electrons in the 3 2p orbitals. So 1, 2 in the first 2p, 3, 4 in the second 2p, 5, 6, in the third 2p. So you'll notice here the first energy level has 2 electrons and it's full. Then the second energy level would have 8 electrons and it is full. Here are the 8 electrons in the second energy level, so it's full. Now we're going to start drawing some diagrams, and I'm not going to show every energy level. I'm just going to show the outermost energy level, just the outermost energy level. And you'll see that outermost energy level is full when we have 8 electrons. So we're going to draw a little bit of a different diagram here. We're going to start to show what are called dot diagrams, and we're just showing the outermost valence electrons. And we're going to imagine that there are 8 spots to fill those 8 positions for that full energy position, that full energy level, I should say. And we're going to place these 8 open spaces around our symbol, 2 on each side of the symbol. So neon would have 1, 2, 3, 4, and then I'll start to double them up, 5, 6, 7, 8 valence electrons. And I've put 2 on each of the 4 sides of the symbol. That's a full outer level. That's a full octet. Octet means 8. And this is what all the other elements are trying to achieve. They're trying to achieve this octet, except for helium. Now helium, the 1s2 is full. Helium and hydrogen, I should say. Helium and hydrogen, all they need to do is fill their first energy level with just 2. So helium would just have 1, 2. Hydrogen has only 1, but it would like to get another one if it could in order to be full like helium. It'd like to fill that first energy level. So we talk about an octet rule. The only exception is helium and hydrogen, and we call that a duet. Duet is 2, okay? But everybody would like to have an octet, a full outer energy level, okay? So what we can do is we can show how, these are just showing the different orbitals and where those electrons are. So for example, for fluorine here, fluorine is going to have 2 electrons in the 1s, 2 electrons in the 2s, and then it starts to fill the 2p, and it has 1 empty spot right there. Okay, it has 1 empty spot. Well, if I was to draw the dot diagram for fluorine, I would draw it like this. I'm not going to show the first energy level. I only want the outermost energy level. And it has 1, 2, so 1, 2, and then 5 more in the p orbitals. 3, 4, 5, 6, 7. A total of 7 in the second energy level. This is the dot diagram for fluorine. Notice there's an empty space right there. That's because it has 1 more spot right there in that 2p orbital where it could take another electron. All right? So what happens if another fluorine comes along? Another fluorine that has the same configuration, and it has 1, 2, 3, 4, 5, 6, 7 outer electrons, valence electrons as well, and if they bump into each other, they might say, you know what, let's make a deal. I would like to fill my space right there, says fluorine number 1, and fluorine number 2 says, yeah, I would like to fill my spot there as well, and then I could have a full outer shell likewise. And so then they bump into each other, they both start to pull on electrons from the other guy, hoping they might fill that empty spot, and they both say, you know what, we are pulling with the same strength, we're never going to beat each other, let's just share. Okay? So what they do is fluorine number 1, who has 1, 2, 3, 4, 5, 6, 7 valence electrons, and fluorine number 2, who has 1, 2, 3, 4, 5, 6, 7 valence electrons, they decide to share 1 each, and they come together like this. And they're sharing a pair of electrons right there. One of those electrons was originally from fluorine number 1, and the other electron there that's being shared was from fluorine number 2. But now they don't care. They don't care. It's like, let's just share them equally, and we both will count it as our own. So now how many electrons does each fluorine have? Counting the shared ones? Well, this one has 1, 2, 3, 4, 5, 6, 7, 8. And the other fluorine, counting even the shared ones, 1, 2, 3, 4, 5, 6, 7, 8. They both have an octet by agreeing to share. And as a result, by sticking together in a compound, they have a full outer energy level and they're more stable. They're at a lower energy position and they're better stuck together, bonded together, than by themselves. Okay? The same is true here. Let's take hydrogen and chlorine. Hydrogen has one electron in its outer energy level, so I'm just going to put one dot there. Chlorine, let's not count the first energy level. Let's not worry about the second energy level because the valence electrons are in the third energy level. So chlorine, how many does it have? 2, 3, 4, 5, 6, 7, just like fluorine. But these are in the third energy level, but we don't care. Those are the valence electrons. It also has 1, 2, 3, 4, 5, 6, 7 valence electrons. Hydrogen and, sorry, this is Cl. Chlorine, they bump into each other, and hydrogen says, man, I would love to have one more electron to fill my first energy level. Chlorine says, I want one more electron to fill my third energy level. And guess what? You're right. They come to an agreement. Hydrogen says, here, I'll share my 1. Chlorine says, okay, great. I will share 1 of my 7. And now, you'll see here, these two shared electrons, they both count as their own. Hydrogen has 2, and it can count its first energy level as full. Chlorine has 8, and it can count its third energy level as full. And they stay together because they both are pulling on those shared electrons, but not so unequally that they, form ions. They share, they may be a polar covalent, they may share somewhat unequally, but still they're sharing enough where they both can count those shared electrons and they stay bonded together. They stay bonded together. Okay? I already mentioned the exception to the octet rule. When you have hydrogen and helium, they're looking for a duet. They're just looking for 2 electrons to fill that outer energy level. Okay? Now, I have shown you how to write these electron dot diagrams. You just place dots around the chemical symbol, and you have 8 positions to fill that outer energy level. We don't know if we're filling the second energy level, the third, the fourth, or fifth. Well, we do, but it doesn't matter. We're just thinking about the outer energy level, okay? Now, here's the neat thing. On the periodic table, on your periodic table, every group is going to have a given number of valence electrons, and therefore they are going to have a similar dot diagram. Everything in group 1, here, on the periodic table, everything in group 1, they just have 1 valence electron. Remember, they end in something S1. They have 1 valence electron, which means everything in group 1 is going to have a dot diagram similar to this. X is just representing some symbol. So, for example, sodium, the dot diagram is just the symbol with 1 dot. It doesn't matter what side you put it on. Okay? So group 1 is always going to have 1 dot on their dot diagram. If you're in group 2, all of these in group 2, again, we only are concerned about the valence electrons. Group 2, they all have 2 valence electrons, 2 outermost electrons. So their dot diagram is always going to have 2 dots around it, like this one, magnesium. And we're going to put them on opposite sides because electrons kind of repel each other. Okay, so we don't start to double them up until we have to. 3, if we come all the way over here to group 13, they have 3 valence electrons. We're not going to talk about the transition elements right now because there's too many exceptions in that. 3 dots around it. Again, you spread them out. Group 14, I'm going to put the group here. Group 14 has 4 valence electrons. You put 1 on each side, you spread them out. That would be like carbon. Group 15 has 5. Now we start to double them up. 1, 2, 3, 4, 5. 16, group 16 has 6. Group 17 has 7, and group 18 has 8, and those are your noble gases. Okay, remember everything's trying to get to that point of being an octet. Everybody wants 8 valence electrons to be full. All right, So when I refer to the electron dot notation, it may also be called the Lewis dot diagram because it's named after a scientist whose name is Lewis. Okay, so Lewis dot diagram or electron dot diagram is basically representing the number of valence electrons around an atom of a particular element. Okay, and we can use that to show compounds, how they come together and share those electrons. So here you have a molecule of hydrogen. Hydrogen has one valence electron, another hydrogen has one valence electron. They come together and they decide to share, and you'll notice here, they both are deciding to share one of their valence electrons, so now they both can count those shared, that pair of shared electrons as one of their own. So hydrogen has two, and this hydrogen has two, and they're both happy. Okay? I already showed you fluorine. All right? Now instead of a pair of electrons here between the two atoms, we also might just put a dash. That dash right there is representing two shared electrons. So you might see two dots that are showing you a pair of shared electrons, or we might just put a dash like that, and that is two shared electrons. So either one is fine. Okay? If you're sharing two electrons, that's a single bond. A single bond is when you're sharing a pair of electrons. A pair of electrons. A double bond means you're sharing two pairs, that'd be four electrons. And a triple bond, you're sharing three pairs, that's going to be 8 electrons. Sorry, 6 electrons. 6 electrons, okay? 6 electrons. All right, so let's talk a little bit about how we draw these different Lewis structures for atoms. All right, I'll walk you through the steps here. Actually, let me walk you through this one right here. Okay. How do we draw these Lewis dot diagrams, not just for atoms, but now also for compounds? Also for compounds. Well, here's what we do. Basically, we look at the chemical formula that is given to us. In this case, it's CH3I. And usually the first element is the one that is going to be in the center if there's more than one element in the compound. So we're going to assume that C is going to be in the center of our compound. But the first thing we need to do is we need to think about how many electrons, how many valence electrons are going to be represented in our diagram. Okay? So individually, let's look at carbon, iodine, and hydrogen. And all we do is we draw the dot diagram for each of them. Carbon is in group 14, so it has 4 valence electrons. Iodine is in group 17, so it has 7 valence electrons. Hydrogen is in group 1, so it has 1 valence electron. Okay? In our formula, you'll notice that we have 1 carbon. See this 3 here? This 3 right after the H, that means you actually have 3 H's. So there's going to be H but times 3 here. And we have 1 iodine. Okay, so that's all we're doing right here, is we're taking the hydrogen and multiplying by 3. So we're actually going to have 3 of these hydrogens. I'm just going to write it 3 different times, okay? We're going to have 3 of these different hydrogens. All right? Now what we do is we are going to take the first atom, carbon, and we're going to place it in the center. So here's my carbon, and I'm going to put its 4 valence electrons around it. Now what would it like to do? It would like to fill the other 4 spots. Remember, there are 4 spots there for it so that it can get an octet. Well, how is it going to fill those other spots? Well, hydrogen has 1 electron that it can share, and that hydrogen has an electron, and that hydrogen has an electron. So the hydrogens are going to come in here and say, you know what? Take my electron and we'll share it. Here, take my electron and we'll share it. Here, take my electron and we'll share it. Okay? The iodine has 7 electrons, but look at this one right here. See this one? It's all by itself as far as a pair goes. It doesn't have another one to be paired with. So iodine says here, I have 1 that I can share, and I'll hold on to my other 6. But now look at everybody. Let's just see if everybody is happy according to the octet rule or the duet rule. Let's look in the middle, carbon. And you count even the ones that are being shared as part of that atom. So carbon, I'm going to put a circle around all of carbon's electrons, even the ones that are being shared by other atoms. 1, 2, 3, 4, 5, 6, 7, 8. Carbon has an octet. Carbon's happy. Let's look at iodine. Iodine, 1, 2, 3, 4, 5, 6, 7, 8, even counting the ones that are shared. It is happy, octet. Hydrogen, 1, 2. Hydrogen, 1, 2. Hydrogen, 1, 2. It has its duet and it is happy. Everybody now is more stable and everybody is a little more content to be in that compound rather than by themselves. Okay? Now you can draw, as I mentioned, these shared pairs. You can represent them with a dash as well. So that means exactly the same thing. A shared pair is the same thing as a dash. You have to remember that this dash represents 2 shared electrons. Okay? Let's try one here. Let's do the Lewis structure, the Lewis dot structure, dot diagram for NH3. Okay? And all you have to do is think about on the periodic table, where are these on the periodic table? So if I look at nitrogen on the periodic table, that is in group 15. So it has 5 valence electrons. So nitrogen's symbol is going to look like this. 1, 2, 3, 4, 5. It has 5 valence electrons, and look at this. It has 1, 2, 3 spots that it would like to fill. Okay, it would like to fill those 3 spots. Hydrogen is in group 1, so it has 1 valence electron, and it looks like that. Okay, remember it's a duet. It has 1 spot right there that it would like to fill. Well, nitrogen says, you know what, hydrogen, come in here, let's share our electrons, and if you've got 2 buddies that can come in and fill my other 2 spaces, that would be wonderful, and that's exactly what happens. So, one molecule, this molecule has 1 nitrogen atom and 3 hydrogen atoms, and each nitrogen atom has 5 valence electrons. The hydrogen atom has 1 valence electrons, so there's a total of, how many total are there? There's a total of 8 valence electrons available for bonding. Here's what we're going to do. You put the first one in the middle, the first element symbol in the middle, and then around it we're going to put our hydrogen. Nitrogen has 1, 2, 3, 4, 5 valence electrons. Hydrogen comes in with its 1 on 3 sides. The 3 hydrogens come in on the 3 sides. Everybody's happy. Look at the hydrogen. Duet, duet, duet. Look at the nitrogen. Octet, and everybody's happy. Okay? Everybody's happy. Okay. Now, I mentioned double bond. A double bond happens when you're sharing not just 1 pair, but 2 pair, as is shown right there. Okay? So in some cases, in order for everybody to be happy with their octet or duet, there needs to be a double bond. And I'll show you exactly how you will know if there's a double bond or not. Or they might have to share 6 electrons. In that case, that would be a triple bond. That would be a triple bond. In these cases, a double bond is stronger than a single. A triple is stronger than a double. The bond length gets shorter and shorter the more multiple bonds you have there. Okay? And here are some bond energies for single, double, triple. You can see how much the bond energy increases and how the bond length decreases when you have multiple bonds. Okay? All right. I'm not going to ask you necessarily about resonance, so you don't have to worry about that. But I will show you how to determine if you're going to have multiple bonds or not. Okay, so let's look at this one right here. Here we have a structure called methanol, CH2O. And again, we look at the individual atoms. So we have 1 carbon, has 4 valence electrons. We have two hydrogens, each have one valence electron. I'm going to just put another hydrogen here. And then we have an oxygen. An oxygen has 6 valence electrons. So each of them individually are drawn like that. Okay? Now, if we build our molecule, the first atom here is going to be in the center. So I put carbon in the center. And then I'm going to place my oxygen and hydrogen around those. Now, look carefully, please. Watch. Carbon, I'm going to build it as we go here. Carbon has 4. 1, 2, 3, 4. Okay? Hydrogen has 1 each. So I'm just going to put the hydrogen on one side here, there, and there. Hydrogen's happy now. It has its duet. It's sharing 1 from carbon and it has its own. So it has 2. It's fine. Oxygen now has what? Oxygen has 6. So it's going to come in here and it's going to look to share. So it's going to, let's just put it here for now. 1, 2, 3, 4, 5, and 6. It's going to share 1 with carbon. Well, let's see if they're happy. Doesn't look like it. Hydrogen has a duet. Hydrogen has a duet. It's happy. Okay, that's fine. But carbon, look, it still has this space up there. And oxygen still has a space there. They're not happy. They don't have their octet. So carbon and oxygen, they get together and say, you know what? We have to do a little bit more sharing. We're sharing a pair. That's good. That helped me. We're sharing 1 pair right here in the middle. But carbon and oxygen say, you know what? We're going to have to share another one each. We have to share another one each in order for both of us to be happy and count the shared electrons as our own to get our octet. So what they decide to do is they decide to take that 1 more electron there that was by itself and bring it into the shared area. Bring that into the shared area. And now what they do is they've got carbon, as I mentioned, hydrogen, hydrogen, oxygen. And now carbon says, I brought this other electron down here. And oxygen says, okay, then I'll bring my other electron in there. So in addition to the ones that they were sharing before, the pair, now they're sharing another pair. Okay? And carbon and oxygen are going to be much happier now. Let's double check the numbers. Hydrogen, duet. Hydrogen, duet. Carbon, look. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. It's happy. Oxygen, because now they're sharing 4 instead of just 2. 1, 2, 3, 4, 5, 6, 7, 8. Everybody's happy. This double bond was necessary in order to make sure everybody had an octet. They had to share not just 1 pair, but 2 pair. Not just 2 electrons, but 4. Okay? So here we have a pair that is shared, a pair that is shared. Here we have 2 pair that are shared. You'll notice a single dash means 1 pair, single dash means 1 pair, a double dash means 2 pair, 4 electrons that are being shared there. Okay? All right. Let's talk a little bit about now ionic bonding, and let's talk about how this happens to form an ionic compound. So with ionic bonding that forms ionic compounds, what's going to happen is there's going to be a transfer of electrons because the pull from one atom is so much greater that it basically pulls the electrons from the other all the way over to the first atom and causes the 2 atoms to become ions, charged particles, because now they don't have equal number of electrons and protons in each of the atoms. And then you have opposite charges, ions, that are going to hold each other together, be attracted to each other. Okay? So you need to have this understood, and in your notes, an ionic compound, it is made up of positive and negative ions. Again, how are those ions formed? One atom pulls so strongly on the other's electrons that there's a transfer of electrons, and then there are ions that are created. And those positive and negative ions then are going to be attracted to each other, pulled in. The total charge on the whole compound is going to be neutral. In other words, the positive and negative charges are going to be basically opposite but equal. and you can have an overall neutral charge, but individually you've created ions. Let me show you what I mean. For example, sodium is a metal and it likes to give up its electrons if it can, whereas chlorine is a nonmetal, likes to gain electrons in it if it can. If they come into close contact with each other, let me just show you what I mean here. Sodium, let's do the dot diagram for sodium. Sodium has 1 valence electron. Chlorine has 7, okay? But the deal is, chlorine has such a stronger pull on electrons, has such a much higher electronegativity, that when these two get close together, sodium and chlorine don't share electrons. Sodium basically says, man, take it. You're going to pull it so much more strongly than I do. Sodium is going to give up its electron. Chlorine is going to take the electron. And now what happens is, sodium has lost its 1 valence electron. It's lost an electron. It now has 1 more proton than the total number of electrons, and it becomes a positive ion, a cation. Chlorine gained this electron. It now has 1 more electron than the number of protons. It was neutral before, and now it becomes Cl negative. The positive and negative, one of each, come together. Those are attracted to each other to form NaCl. Notice I don't write charges anymore. Once they come together, they don't have, the overall compound doesn't have a charge on it. But initially it was the stripping of an electron and the adding of an electron that gave them charges, opposite charges, and they come together in the right ratio to form a neutral compound. Okay? The formula unit is what we refer to as the simplest collection of atoms that form an ionic compound. It's no big deal. So let me show you just a couple examples here. I showed you just sodium and chlorine right here. This is exactly what happens. The sodium basically loses its electron to the chlorine, forming a cation, a sodium cation, and the chloride, notice the ending here, we'll talk about that later, but the ending for an ion changes for the non-metals. It goes IDE. That becomes negatively charged, and they come together, they bond together, they're attracted to each other now. 1 sodium ion, 1 chloride ion, each are going to come together, a +1 and a -1 come together in a 1-to-1 ratio to make a neutral ionic compound. Okay? Whereas if you've got calcium, calcium is a metal that has 2 valence electrons, 1, 2. Fluorine is a nonmetal, they each have 7. So notice there's a space right here. There's a space, there's a space. Fluorine has a large electronegativity. In fact, it has the highest electronegativity of all the elements. Calcium has a lower electronegativity. So calcium is willing to give up that electron and this electron. But if it bumps into fluorine, each fluorine is only going to take 1. It doesn't want 2. It just wants 1 because it has 1 space there in its octet. So you're going to need 2 fluoride ions to accommodate just the 1 calcium. All right? So this calcium right here, this is a calcium ion, or sorry, calcium atom, has 2 valence electrons. And this is fluorine. It has 1 valence electron each. They each have 1 valence electron. So basically, calcium gives up its 2 valence electrons. It gives 1 to the first fluoride ion, or fluorine atom, and it gives 1 to the other fluorine atom. So they each are happy now, but it had to have 2 fluorine atoms because calcium has 2 valence electrons that it wants to give up. So this is your calcium ion. This is your ion, and it has a charge of 2+. This is an ion, but it has a charge, each have a charge of -1. So you're going to need 2 fluoride ions to match up with just 1 calcium, and this is CaF2. Notice the 2 right there. Why did I need 2? Because each fluoride ion is only a -1. The calcium is a +2. You're going to have to make sure they come together so you have a total neutral compound now. Okay? If you want to figure it out, here's a little trick. Calcium has 2 valence electrons that it likes to give up, so it forms a 2+ ion. Fluoride has 7, likes to gain 1, becomes a -1. If you want to know what ratio they combine in, just take the charge from this one and that becomes basically the number of fluorine atoms, and the charge from this one, that's a 1 negative. Take the absolute value of that, and I don't write a 1 usually, but I'm going to put it there. The opposite charge, the charge on the opposite ion, is going to tell you how many of the other one you need. So it just kind of tells you what ratio they need to combine in. You have to get a neutral compound. You have to make sure that the numbers here on the ions, the total ion charge, they come together in a ratio so that you get 0 when you add them together. Okay? When I say lattice energy, I think I mentioned this before. It's just basically it's the energy that's keeping the arrangement of those ions together. Okay, and basically, if you were to pull them all apart, that's how much energy you need to pull apart all of those bonds. Okay. Okay. Basically, when we talk about ionic bonds versus covalent, remember molecular means covalent. Okay, there are some differences here between ionic and covalent. All right, there's a couple things that I want you to understand. All right, melting point. Ions in an ionic solid, those bonds are very strong. Okay, so all that means is that when I say molecular, remember this is covalent. Covalent, when you're sharing electrons, the bonds are not as strong as ionic, so they melt at lower temperatures. Covalent melts at lower temperatures than ionic. Basically, all of these properties are a result of saying that an ionic bond, ionic, is stronger than covalent. If you remember that, then all these other properties make sense. Boiling point then, how much energy is it going to take to pull them apart? Well, similar to melting point, boiling points for molecular compounds are also at lower temperatures. All right? They are going to start to turn into gases at lower temperatures as compared to ionic bonds. That's why many of the molecular compounds are gases. They're already gases at room temperature. Okay? Hardness, ionic bonds are stronger, so strong ionic attractions, ionic compounds are hard. Solid forms, okay? All right. Deform, can you deform things? Ionic compounds, if you do break them apart, they're going to kind of slice and be brittle. So they're going to be brittle because those charges are going to kind of push each other away once you do start to break them apart. Okay. Whereas covalently bonded compounds, they can be deformed. They can be kind of maybe, if they're solids, can be reformed, reshaped. Okay. Electrical conductivity. Molecular compounds do not conduct electricity normally. Remember, there aren't any charges there. They're sharing the ions equally, so there's not a positive or negative end to the compound. Whereas ionic compounds, they do conduct electricity if they are dissolved in water or if they are melted, because then you're freeing up those ions. Let me repeat that. Compounds, molecular compounds, do not conduct electricity. Ionic compounds also do not conduct electricity because the ions are stuck together. They're not moving. But if you take those ionic compounds, if you take, for example, salt, sodium chloride, as a solid, it's not going to conduct electricity. But if you put it into water, then those are going to be split apart, and you're going to have these charged particles in water. Now they will conduct electricity. Okay? They will conduct electricity. Ions are then free to move and conduct electric charge. Okay? Now, one other thing when we talk about ionic and covalent is this idea of a polyatomic ion. I want to show you something really quickly here. Here you have NH4. Notice there is a charge on that entire group, not just an individual element, but the entire group. This entire group is covalently bonded, sharing electrons here, sharing electrons, sharing electrons, sharing electrons. But for the entire group, in that entire group, if you count up all the protons in that group and all the electrons in that group, notice here, the plus, there's one more proton than electrons. So the overall charge on that is a +1. The nitrogen and the 4 hydrogens are all covalently bonded, but the whole group has a charge on it because there's an unequal balance between electrons and protons. Okay, same thing here. All of these, this is a covalently bonded group, but because it has a charge, it is called a poly. Poly means many, atomic atoms, many atoms ion. It's not just a one atom ion like sodium ion or chloride ion. It has many atoms in there bonded together covalently, but you don't have the same number of electrons and protons in the whole group, so there's going to be a charge on it, either positive or negative. Okay, and we'll talk about some of those names. You'll be given a list of polyatomic ions that you can always refer to, so you don't have to memorize them. Okay, metallic bonding. All I'm going to ask you about metallic bonding here, all I want you to understand is that metals, basically the electrons can move freely. Electrons can move freely through a metal, and that's why they have some of these properties. When I talk about metallic bonding, all you need to know is that there are electrons that move freely. And what can they do, therefore? They can conduct heat. They have a shine to them. They are malleable, meaning you can reform them. You can pound them into thin sheets like aluminum foil. They're ductile, meaning you can stretch them out into a wire. Okay? That's all I want you to know there. I want you just to know that metals have free-flowing electrons and have these different properties. Okay? Okay, now we're going to come to 6.5, and this is a very, very important section here. We're going to talk about molecular geometry. All that means is the shape. What is the 3D shape of these molecules? Okay? So in molecular geometry, what we're going to be looking at is we're going to be looking at the shape of the molecule. The shape of the molecule has a lot of influence on the properties of that particular compound. Molecules are not flat. We draw them on a piece of paper, we draw them flat, but they're three-dimensional. So we want to look at the potential 3D shape of some molecules, okay? And how we can kind of get an educated estimation of the shape based upon what we know about electrons and how they bond and how they work, okay? So here is your underlining idea or principle when considering the shape of a molecule. We're going to call it the valence shell electron pair repulsion. And basically that is just VSEPR. We put it all together and we say VSEPR, the VSEPR theory. It basically says this, that repulsion, or basically, repulsive forces pushing each other away between sets of valence electrons surrounding an atom kind of determines the shape of that molecule, of that compound, okay? Because they're going to push as far apart as possible. They obviously aren't going to push so far apart that they leave the atom, but they're going to arrange themselves around that central atom and give each other space, those electron pairs. Remember, each orbital is going to have 2 electrons, okay? So we kind of think of them in pairs often. All right, here's the underlying idea. Here's how you come up with the shape of these different molecules. And I'm going to show you exactly how to do this. And we'll look at different shapes and show you how it is determined, okay? So let's say that we have this molecule right here, BeF2, beryllium fluoride. Beryllium fluoride, what we do is we draw the Lewis dot diagram for it, and then from that we're going to consider a chart, and we're going to determine the shape of that compound by looking at the chart and how the electrons spread out around the central atom right here. So what we do is we look at beryllium, and we look on a periodic table. Beryllium is in group 2, so it has 2 valence electrons. Beryllium has 2 valence electrons. Fluorine has 7 valence electrons. It's in group 17. So if beryllium and fluoride or fluorine want to combine together, this is a metal, this is a nonmetal. By the way, ionic compounds are always between a metal and a nonmetal. Okay, a nonmetal and a metal. So here we have a metal and we have a nonmetal. So we're pretty guaranteed that this is going to form an ionic bond. How is that going to happen? Fluorine is looking to fill that space right there. And beryllium says, I can help you. I have I have 2 valence electrons, but I'll give you 1. And beryllium says, hey, I got another one. Fluorine, do you have a friend? Fluorine says, okay, I'll call over my other fluorine buddy here. He has a space there as well. Beryllium says, okay, you can have my other valence electron. So the 2 fluorine atoms gain an electron each. They become fluoride ions. Each of them are going to be, negative ions here, negative ions. The beryllium lost electrons. It becomes Be2+, and you need the same number of negatives as positives to make a neutral ionic compound. So they come together as beryllium fluoride, BeF2. Here's how they look in a structure though, when we draw the Lewis dot diagram of it. We put beryllium, it's right here, but I'll redo it. We put beryllium in the center, and the 2 fluoride ions, or fluorine atoms on the either end, and they're sharing pairs in between the atoms, like that. If you have this situation, if you have a central atom right here, and you have 2 pairs, 2 regions where there are bonds, you are guaranteed that the shape of this is going to be what we call linear. It's just going to be straight. Okay, there's no bend to it. There's not really 3-dimensional. It's just a straight linear shape. Okay, 2 regions around the central atom, 2 bonding regions. Here's a bond here, here's a bond there. I could also draw it like this. Bond, bond. Shared pair, shared pair. If you got 2 of those, and that's it, it's definitely going to be linear. Okay? If you have 3 of them, in this case, boron and 3 fluorine atoms, you've got 3 bonds. 1, 2, 3. If that's the case, then the shape that you're going to have is called trigonal planar. Planar means it's flat. It's flat, but there's 3 atoms around the central atom. So there's 3 fluorines around the central boron one. So those are going to be basically trigonal planar. Okay, like this right here. When you have a linear, like we talked about before, the angle between the 2 bonds is 180. The angle between these bonds is 120. It's a circle 360 divided by 3, right? Okay, and then another one here, if you've got 4, well, actually, it's not going to be 90 degrees. These aren't going to spread out on a piece of paper because they can actually go 3-dimensional now. The best way for them to spread out is not to stay flat. They would only be 90 degrees apart. It actually is better for them to go now 3-dimensional. And there's going to be angles like that. 1 can go up, 3 can kind of point down, and this is called tetrahedral. Tetrahedral because now the angle between those is 109.5 instead of 90. They want to spread out as much as possible. Okay, so when you get 4 bonds, now they start to go 3-dimensional, and that is called tetrahedral. Okay. Okay. Now we're going to talk about what if there are bonds, and there's also a region where there's no bonds, but there's just a pair of electrons, just by themselves, not bonded to anything because you've got these extra electrons. Let me show you what I mean here. Let's go to NH3. Let me show you how this Lewis diagram is formed. You have to draw the Lewis diagram first. So nitrogen has 5. It's in group 15. 1, 2, 3, 4, 5. Remember, you don't pair them up until you have to. 1, 2, 3, 4, and then pair them up. The fifth gets paired up. Hydrogen has 1 each, and I've got 3 of them. So hydrogen is going to come in here, share its 1. Hydrogen in here, share its 1. Hydrogen in here, share its 1. Now, here's the case. You've got 3 bonds, 1 lone pair. By lone pair, I mean there's no bond there. Well, what's the shape going to be? The shape is still kind of like up here. You notice? It's still going to be kind of like this, but now this lone pair actually takes up a little bit more space and pushes these bonded areas down a little bit. The angle is going to be a little bit different here, but it's still kind of like a tetrahedral. But the shape of the molecule, remember, there's no atom up here. There's no atom up here now. These are just a lone pair of electrons. So there's no atom up there to talk about the molecular shape. The shape that we call this is a trigonal 3, right? Three sides here, pyramidal. So it's like a pyramid that has 3 legs to it. Okay? There's no atom up here. It's just a lone pair of electrons that's pushing, that it wants to repel, it wants to push those other electrons that are in bonds, pushes them away. Okay? Here's one that you must know, the bent shape, or angular or bent. I call it bent. But here, let me do it with water. We have oxygen. Oxygen it is in group 16, so 1, 2, 3, 4, 5, 6. Okay? Has 6 pairs, or 6 electrons, valence electrons. Hydrogen has 1. So it comes in here, and it comes in here. Now you would think, oh, this is just going to be linear. But what happens is these lone pairs right here like to take up more space, and they end up pushing the bonded regions down. So it's not just going to be linear. It's not going to be linear. If you see 2 bonds and a lone pair, or in this case 2 lone pair, you're going to end up getting a bent shape. So it actually ends up looking like this. These lone pairs come up here and try to take up space and push the bonded regions down like that. That is called bent or angular. And water is a very, very popular one. Here's your shape, here's your model, but remember there are lone pairs up here. That's what this is showing. This is showing the electron region shape. Here's electrons, bonded electrons, but the molecular shape, just the atoms, give us a bent shape. Okay? So all you need to do, here's what you need to do in order to determine the shape. It's real simple. All you need to determine is, after you draw your Lewis structure, the atoms that are in bonds and the electrons that are in bonds, and the number of lone pairs of electrons that are not in bonds. And then all you do is you match it up to this table. Okay? So let me show you a quick example here. Let's take this one right here. Okay? Actually, let's do this one. Yep, let's draw this one here. Okay, so let's say you have ClO3 negative. Now this is a polyatomic ion. Many atoms, and it has a charge on it. CiO3. So all we do is, carbon has 4 valence electrons. It's in group 14. Iodine has 7. Okay. Oop, I'm sorry. This is chlorine. This is not Ci. This is a Cl. My apologies. This is Cl, chlorine. So it has 7. Okay. And oxygen has oxygen has 6. Okay. All right, it has 6. So what we need to do is we need to count up the total number of electrons that we're talking about here. Let me restart this. I'm going to put down my central atom, and the first thing I'm going to do is going to draw kind of a skeleton structure. So here's my central atom, chlorine, and I'm going to put 3 oxygens around it. 1, 2, 3 oxygens. Okay? I need to figure out how many total valence electrons I'm going to be talking about. Chlorine has 7. Each oxygen has 6, so that's 3 times 6, that's 18. But look right here, see that negative? That negative means it has one extra. So it means it has 26 valence electrons that I have to account for. Okay? I have to account for 26 valence electrons. So here's what I do, is I put them around the outside atoms first, and then I end up on the central atom. So 26. I already have 2 with that bond, 4, 5, 6. Let me repeat. I did my central atom here, and I did a single bond to all 3 oxygens. Now I need to fill in the other valence electrons. How did I get these numbers again? 7, chlorine's in group 17. Oxygen is in group 16, and there are 3 of them. 6 times 3 is 18. And then the -1 tells me I have an extra one. Okay? So that is 26. I already have 2, 4, 6 here. Now let's continue. 7, 8, 9, 10, 11, 12. Octet. 13, 14, 15, 16, 17, 18. Octet. 19, 20, 21, 22, 23, 24. Octet. What do I do the next 2? I put them around the central atom. 25, 26. Does everybody have an octet? Yep, octet. Remember this bond counts as 2. Octet, octet, and octet. They're happy. That is the diagram, the Lewis dot diagram for that particular polyatomic ion. And then you would put maybe brackets around it and put a negative there. Now let's talk about the shape. All you do is this. Here's how simple it is. You look at this and you say, okay, you got 1, 2, 3 bonds, 1 lone pair. You go up to your chart. What do? You will fill this in, 3 bonds and 1 lone pair. Where is that? 3 bonds right here. Bond, 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 lone pair. 3 bonds, 1 lone pair. Here it is, and it is a trigonal pyramidal. Here's an example for you, which kind of looks like your example right there, the one that we did. And here are some sample compounds, and that is a general form right there. This E stands for a pair of electrons. So AB3 with a lone pair of electrons. So all you have to do, let's fill in this table here. This would be 2 bonds, 0 lone pairs. This would be 1, 2 bonds, 0 lone pairs. Oh, sorry, 1. Sorry, 1 lone pair. Okay? Yeah, looks like you got a 1 lone pair there. Okay? Here you've got 3 bonds. You know what? This should be different. I apologize. This one should be bent. That is bent or angular. They have these wrong here. Okay? Please change that. This is 2 and 1. This is 3 and 0. This is your trigonal planar. Okay? Please change that. This one is 4 bonds. 1, 2, 3, 4, and no lone pairs. That's tetrahedral. Here you've got 3 bonds and 1 lone pair. There's your lone pair. That is trigonal pyramidal. Here you've got also bent, and that would be 2 bonds and 2 lone pairs. That would be like water, and that would be 2 and 2. That also is bent. Here, this is one we didn't talk about, but all you have to do is refer to it. This is where you've got 1, 2, 3, 4, 5. This is not too popular, not very, not because this is an exception to the octet rule, so this is not a really popular one. But all you have to do is say, oh, if it has 5 bonds around that central atom and no lone pairs, just look at that and write it down. Okay. And then the last one, again, this is an exception because this is breaking the octet rule, but if you're able to have 6 bonds around a central atom, 6 with no lone pairs, that is called octahedral. Okay? All right, I'm not going to ask you about hybridization, so you can skip anything that talks about hybrid orbitals. Don't worry about that whatsoever. Okay? Now, one last thing before we wrap this chapter up. One last thing is I do want to talk a little bit about what are called intermolecular forces. Okay? Intermolecular forces, and then we'll wrap this up here. Intermolecular forces basically are the forces that are going to hold one molecule close to another molecule, like in liquids and solids. Gases, obviously, they're very far apart, okay? But inter, between molecules. In water, what is holding one water molecule to another water molecule? What is the attraction between those two so that water is somewhat cohesive? Well, that's what intermolecular forces do. So let's talk about those. I'm not talking about now the bonds that hold the hydrogen and the oxygen together. I'm talking about one water molecule and another water molecule. What is keeping them attracted? Okay? All right. Well, in order to keep one water molecule attracted to another molecule, there has to be something positive in this molecule that is attracted to something negative in that molecule. Something positive in this molecule attracted to something negative in that molecule. In order to have a positive and negative in a molecule, even though the whole molecule is neutral, this water molecule is neutral, but there's a positive end to it and a negative end. Remember, there's an unequal sharing of electrons because one pole is greater to one side. So this oxygen has a greater electronegativity, so it's going to pull the electrons closer to that side. And therefore, the electrons are going to hang out more on this side of the molecule, even though the whole molecule is neutral. So this side is going to have a negative end, leaving the other end to be more positive. Well, that means if this positive end of this molecule comes close to the negative end of another water molecule, they're going to be attracted to each other. And that's what forms an intermolecular force. That intermolecular force can be to different degrees. They can be really strong or they can be really weak. And that's all we're going to talk about now. So this dipole is the difference, the imbalance in electrons. Hey, electrons are really pulled to one side. That side of that molecule is more negative. The other side is more positive. And sometimes we'll draw an arrow like this toward the more negative side, and this would be the more positive side on that side. Okay? These are called dipoles. Dipoles are when you have one side of the molecule is more negative because the electrons spend more time there. Okay? Because the pull is stronger on that side on the electrons. It doesn't mean then the whole molecule is negative. It just means one side of the molecule is negative. One side is positive. Okay? So, when we have this dipole come close to another dipole, meaning a dipole molecule, then this positive side of the molecule is attracted to that negative side. And we have a dipole-dipole force. Okay? Dipole-dipole force is holding them close to each other. Okay? So here are some examples of molecules that have dipoles in them. I mentioned water already, and water, the dipole is pointing toward the oxygen because oxygen pulls on the electrons a little more strongly. Here you have ammonium, the electrons are pulled more towards the nitrogen. So this side is going to be a little more negative, and where the hydrogens are a little more positive. Okay? Now, if there is an equal pull and there's symmetry, then you're not going to have a dipole. You're not going to have an imbalance in the electrons. They may be pulled in one direction, but then it's equally spread out. So for example, in this one, yes, the chlorine pulls greater on the electrons, but they're pulling in 4 different directions equally. So you're going to have a symmetrical pull, and there's not a lopsided result of positive and negative here. Okay, same thing here. You've got pull in this direction and pull in that direction, and you're going to have an equal pull in both directions. You're not going to have a dipole. No dipole. There has to be one obvious side where the electrons are going to be pulled to, not pulled the same in both directions or in 4 different directions. There's always going to be a dipole if the molecule is not symmetrical. If it is symmetrical, that means all atoms on the 4 sides here are the same, or on both sides are the same, then there's not going to be a dipole. Okay? Okay. So what does that mean? It means that when you have a dipole, you have these intermolecular forces. And the strongest known intermolecular force is hydrogen bonding. Okay? Hydrogen atom bonded to a highly electronegative atom and that always results in hydrogen bonding. When you see molecules that have H bonded to O, or H bonded to N, or H bonded to F, okay, those are going to cause strong hydrogen bonding. So fluorine, oxygen, nitrogen, FON, fun, 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 fun. Now I know it doesn't spell fun, but you can think of it that way, okay? That's going to cause strong dipole moments, which is going to result in strong intermolecular forces. So hydrogen bonding is the strongest intermolecular force, okay? And it happens when hydrogen is bonded to fluorine, oxygen, or nitrogen, okay? London dispersion forces are the weakest intermolecular force, and that simply happens like this. When you have basically no dipole, none whatsoever, like H2, if you have a hydrogen bonded to another hydrogen, they're pulling it with equal strength. There's not going to be electrons on one side and not on the other side, okay? They're going to be equally distributed. But every once in a while, because these electrons are always moving, always moving, always moving, there might be a little shift to one side, and that's going to cause a momentary unequal shift or dispersion of electrons. And then that might cause a little bit of a switch in the spread or the dispersion again, the spreading out of the electrons of the other one, the other H2 molecule next to it. So basically what that means is you have a momentary lopsidedness of electrons on the one, and that's going to cause a momentary lopsidedness on the other. These are very weak though, very weak, and the imbalance is momentary, which causes an imbalance in the next one, in the molecule next to it, okay? So this is a temporary dipole because of the constant motion of electrons, okay? And so as a result, you will have a very, very weak temporary dipole that causes a temporary dipole in the next one, and there's going to be a slight attraction between the two, okay? All right. I know that's a lot to take in. Please do these Chapter 6 review questions, and I give you the answers in this assignment. I'm going to also include a couple other videos in our assignment from YouTube that might help you. Please watch those, and as always, send me questions. Let me know if you have any concerns, something I can help you with. All right? Keep working hard. Let me know how I can help you, and have a great day.